Hello everyone, my name is Cindy Wu. Today I'm very excited to share Motive, our recent work on motion attribution for video generation. Video generation has made remarkable progress. Models like Cosmos, View, and Sara can now produce highly photorealistic videos from text prompts. But there is a persistent gap. These models struggle with motion. Temporal dynamics can be jittery, unnatural, and physically implausible. This raises a natural question. Given a massive training dataset, which training clips influence the motion in generated videos? And here's what we are trying to do concretely. Given a core video, like a floating cube, we want to quantify which training clips positively influence the motion and which ones hurt it. We tackle this problem with data attribution approach. As we know, motion is a defining element of video. Unlike image generation, video must capture how objects move, interact, and obey physical constraints. So, attributing motion in video generated models mainly faces two core challenges. First, motion localization. We need to localize and attribute to motion. And second, scalability. Video generation models and datasets are usually massive, and naive influence approaches are computationally intractable. We introduce Motive. It is a scalable, gradient-based, and motion-centric data attribution framework for video generation models. Motive addresses both challenges in a unified pipeline, and there are two main components: motion attribution for temporal localization and efficient gradient computation for scalability. I'll walk through each briefly. For motion attribution part, we first detect motion with tracker and compute the motion magnitude patches and use them to construct the motion weighted loss. Backpropagating this loss yields the motion aware gradients that capture motion rather than appearance. Given a query video, our goal is to identify which training clips most strongly influences its motion. To make this attribution practical at scale, our approach relies on two key ideas: a single sample estimator and structured projections. We estimate influence by comparing motion aware gradients extracted from training and query videos under the same condition. Estimating influence under the full diffusion training distribution would require averaging over many time steps and noise samples, which is infeasible and expensive. So instead, we fix one shared time step and one global noise sample and use them consistently across all training query comparisons. This compact representation makes gradient computation feasible at scale and produces more stable influence rankings. Structured projections use the fast food transform to compress a full gradient vector into a low dimensional space. And together, these make it trackable to compute influence over millions of training samples. And here's some examples. For floating cube query, the top positive influences are wave, cloud, and water footage. They generally have this smooth and fluid dynamics. Training on those clips increase the probability of generating floating motion. And for negative influence samples, it include cartoon clips with fast, stylized, and inconsistent motion, which decreases the probability of generating target motion. We further test across 10 physically distinct motion types: compress, bounce, roll, explode, and more. We use Motive to select the top K most influential clips given query data, then fine-tune on the curated subset. For spinning coin query, the base model produces inconsistent results. And random selection adds some motion but still noisy, and some parts are flat and barely moves. For our motive selected data, the coin spins naturally. And here are more samples of free fall, sliding, and finally compress. So we further scale to multi-core curation. selecting 10% of data with motive against full fine-tuning and other baselines. On the left, we have quantitative results on V-bench. So motive achieves the highest dynamic degrade while staying competitive on subject and background consistency. It reaches 74.1% human win rate compared with base models. To summarize, motive is the first framework for motion-centric data attribution in video-generated models. It provides scalable influence scores that isolate temporal dynamics from static appearance. Using motive, we can curate data subsets that significantly improve their motion quality. Thank you.